Hello everybody. This is an audio lecture of structure and synthesis of alcohols for visually impaired students. First of all, we will start the introduction. So, alcohols are organic compounds containing hydroxyl OH groups. They are some of the most common and useful compounds in nature, in industry and around the house. The word alcohol is one of the oldest chemical terms derived from the early Arabic alcohol. Originally, it meant the powder and the later essence. Ethyl alcohol distilled from wine was considered to be the essence of wine. Ethyl alcohol, that is grain alcohol, is found in alcoholic beverages, cosmetics, and drug preparation. Methyl alcohol, that is wood alcohol, is used as a fuel and solvent. Isopropyl alcohol, that is rubbing alcohol, is used as a skin cleanser for injections and minor cuts. There are some examples of alcohols are given over here, that are ethyl alcohol, that is ethanol, methyl alcohol, methanol, and isopropyl alcohol, that is propane 2-ol. Alcohols are synthesized by a variety of methods, and the hydroxyl group may be converted to the most of the other functional group. For these reasons, alcohol are versatile synthetic intermediates. In this chapter, we discuss the physical properties of alcohols and summarize the methods used to synthesize them. In chapter 11, Reactions of Alcohol, we continue our study of central role that alcohol play in organic chemistry as reagent, solvent, and synthetic intermediates. Now we will discuss the structure and classification of alcohols. So, the structure of an alcohol resembles the structure of water, with an alkyl group replacing one of the hydrogen atom of water. Figure 10.1 compares the structure of water and the methanol. Both have sp3 hybridized oxygen atoms, but the COH bond angle in methanol, that is 108.9 degrees, is considerably larger than HOH bond angle in water, that is 104.5 degree. Because methyl group is much larger than a hydrogen atom, the bulky methyl group counteracts the bond angle compression caused by oxygen's non-bonding pairs of electron. The OH bond length are about the same in water and methanol, that is 0.96 angstrom, but the CO bond is considerably longer, that is 1.4 angstrom, reflecting the larger covalent radius of carbon compared to hydrogen. One way of organizing alcohol family is to classify each alcohol according to the type of carbonyl carbon atom, the one bonded to the OH group. If this carbon atom is primary, bonded to one another carbon atom, the compound is a primary alcohol. A secondary alcohol has the OH group attached to a secondary carbon atom, and the tertiary alcohol has it bonded to a tertiary carbon. When we studied alkyl halide in chapter 6, we saw the primary, secondary, and tertiary halides react differently. The same is true for alcohols. We need to learn how these classes of reactions are similar and under what conditions they react differently. Figure 10.2 shows example of primary, secondary, and tertiary alcohols. Compounds with hydroxyl group bonded directly to an aromatic benzene ring are called phenols. Phenols have many properties similar to those of alcohols, while other properties derived from their aromatic character. In this chapter, we consider the properties of phenols and that are similar to those of alcohols and note some of differences. In chapter 16, we consider the aromatic nature of phenols and the reactions that result from their aromaticity. So in this slide, we will discuss some examples of primary, secondary, and tertiary alcohol. The examples of primary alcohol are ethanol, 2-methylpropane-1-ol, and benzyl alcohol. Secondary alcohols are, that is butane-2-ol, cyclohexanol, and cholesterol. And similarly, tertiary alcohols are there, that is 2-methylpropane-2-ol, triphenylmethanol, and 1-methylcyclopentane-1-ol. Similarly, we have the examples of phenols. Firstly, our simple phenol, then 3-methylphenol, and hydroquinone. The classification of alcohols are classified according to their type of carbon. that is primary, secondary or tertiary bonded to the hydroxyl group. Phenol have a hydroxyl group bonded to a carbon atom in a benzene ring. Now we will discuss the IUPAC naming of, or we can say nomenclature of alcohol and phenol. Firstly, we will read the IUPAC names, that is alkanol names. The IUPAC system provides unique names for alcohols based on rules that are similar to those of other class of compounds. In general, the name carries the ol suffix together with a number to give the location of hydroxyl group. The formal rules are summarized in the following three steps. Name the longest carbon chain that contains the carbon atom bearing a OH group. Drop the final letter E from the alkane name and add the suffix ol to give the root name. Second rule is the number of longest carbon chain starting at the end nearest the hydroxyl group and use the appropriate number to indicate the position of OH group. The hydroxyl group takes precedence over double and triple bonds. Name all substituents and give their numbers as you would for an alkene or alkene. In following example, the longest carbon chain has 4 carbons, so the root name is butanol. The OH group is on the second carbon atom, so this is a butane 2-ol. The complete IUPAC name is 1-bromo-3,3-dimethyl-butane 2-ol. Cyclic alcohols are named using prefix cyclo. The hydroxyl group is assumed to be on C1. There is some example of cyclic alcohols in this slide. The IUPAC name of that cyclic alcohols are trans-2-bromocyclohexane 1-ol and second is 1-ethyl cyclopropane 1-ol. In this slide there is a problem regarding the IUPAC naming of alcohol. So the question is, give the symmetric IUPAC name for the following alcohol. The solution of this question is the longest chain contains 6 carbon atom, but it does not contain the carbon bonded to the hydroxyl group. The longest chain containing the carbon bonded to the OH group is one outlined by the green box containing 5 carbon atoms. This chain is numbered from right to left in order to give the hydroxyl bearing the carbon atom the lowest possible number. So the correct name of this compound is 3-iodomethyl-2-isopropyl-pentane 1-ol. In naming alcohols containing double bond and triple bonds, use the ol suffix after the alkene or alkyne name. The alcohol functional group takes a precedence over double and triple bonds, so the chain is numbered in order to give the lowest possible number to the carbon atom bonded to the hydroxyl group. The position of the OH group is given by putting its number before the ol suffix. Numbers for the multiple bonds were once given early in the name, but the 1993 revision of IUPAC rules puts them next to the "-ine" or "-ine" suffix. They describes both the new and old placements of the number are shown in the following figures. There are some examples of the compound which were given in this slide with their old and new IUPAC names. The old IUPAC name of the first compound is trans-2-pentene 1-ol. The new IUPAC name of this compound, that is trans-pent-2-ene 1-ol. Second example is the old IUPAC name of the compound is Z4-chloro-3-butene 2-ol. The new IUPAC name of Z4-chlorobute-3-ene 2-ol. Old IUPAC name of that compound is 2-cyclohexene 1-ol. The new IUPAC name of the compound is cyclohex-2-ene 1-ol. Table 10.1 is a partial table showing the order of precedence of functional group for assigning IUPAC names. A more complete table titled Summary of Functional Group Nomenclature appears inside the back cover. In general, the highest priority functional group is considered the main group, the others and treated as the substituent. The OH functional group is named as hydroxy substituent when it appears a structure with higher priority functional groups or when the structure is too difficult to name a simple alcohol. There are some examples of the alcohols are 2-hydroxymethyl cyclohexanone, trans 3,2-hydroxyethyl cyclopentanone, all 3-hydroxybutanoic acid. In this slide there are some problems regarding the IUPAC name of alcohols, so we use above the rule for naming of these alcohols. Now we will read the common names of alcohols. The common name of an alcohol is derived from the common name of alkyl group and the word alcohol. This system picture an alcohol as molecule of water with an alkyl group replacing one of the hydrogen atoms. If the structure is complex, the common nomenclature becomes awkward and the IUPAC nomenclature should be used. There are some examples of compound with their common name and IUPAC name. Firstly, the common name of the first compound is methyl alcohol and the IUPAC name is methanol. Second example is N-propyl alcohol is the common name of that compound and propane-1-ol is the IUPAC name of that compound. Similarly, we have third example, that is isopropyl alcohol. Isopropyl alcohol is the common name and propane-2-ol is the IUPAC name. Allyl alcohol is the common name and prop-2-ene-1-ol is the IUPAC name. Similarly, we have another example, N-butyl alcohol, which is the common name of that compound, and butane-1-ol is the IUPAC name of that compound. Similarly, secondary butyl alcohol is the common name and butane-2-ol is the IUPAC name. Tertiary butyl alcohol is the common name and 2-methylpropane-2-ol is the IUPAC name. Similarly, isobutyl alcohol is the common name and 2-methylpropane-1-ol is the IUPAC name. Similarly, in this slide there are some questions regarding the IUPAC name of the alcohol, so we will use above rules to solve these questions. Now we start our another topic, names of diols. Alcohols with two OH groups are called diols or glycols. They are named like other alcohols except that the suffix diol is used and two numbers are needed to tell where the two hydroxyl groups are located. This is preferred systematic IUPAC name, or we can say IUPAC method for naming diols. There are some given examples of diols with their IUPAC name. First example is propane 1,2-diol. Second example is 1-cyclohexylbutane 1,3-diol. And third example is trans-cyclopentane 1,2-diol. The term glycol generally means a 1,2-diol or vicinal diol with its two hydroxyl group on adjacent carbon atoms. Glycols are usually synthesized by the hydroxylation of alkenes using peroxy acid. The most common example of peroxy acid is MCPBA, which is name is metachloroperoxybenzoic acid. In this slide it is not mentioned about the MCPBA, but I told about this. Second is osmium tetraoxide or potassium permanganate. The synthesis of glycol is reflected in their common names. The glycol is named for the alkene from which is it synthesized. There are some examples like IUPAC name of first diol is ethane 1,2-diol, and in common name we can say it ethylene glycol because it is made from ethene, or we can say ethylene. Similarly, we have propane 1,2-diol IUPAC name and its common name is propylene glycol. Third example is cis cyclohexane 1,2-diol, that is the IUPAC name of that compound, and the common name of that compound is cis cyclohexene glycol because it is formed from cyclohexene. And we already read that the synthesis of glycol is reflected in their common name. Now we will discuss the common names of glycol can be awkward and confusing because the ene portion of the name implies the presence of an alkene double bond, but glycol does not contain a double bond. We'll generally use IUPAC diol nomenclature for diols, but be aware that the names ethylene glycol, automotive antifreeze, and propylene glycol used in medicines and foods are universally accepted for these common diols. Now we will read the names of phenols. How we name or how we nomenclate the phenols. Because the phenol structure involve a benzene ring, the term ortho 1,2 disubstituted, meta 1,3 disubstituted, and para 1,4 disubstituted are often used in common names. The following examples illustrate the systematic names and the common names for some simple phenol. There are some examples. The IUPAC name of the first example is 2-bromophenol, and in common name we can say it orthobromophenol. Similarly, we have second example 3-nitrophenol is the IUPAC name of that compound, and common name is metanitrophenol. Similarly, we have IUPAC name 4-ethylphenol and common name is para-ethylphenol. The methylphenol are called crazoles, while the names of benzene diols are based on their historical uses and sources rather than their structure. We will generally use systematic names for phenolic compounds. There are some examples. First example is with their IUPAC name is 2-methylphenol, and in common name we can say it orthocresol. The second example is benzene 1,2-diol, which is the IUPAC name of that compound. In common name we can say it catechol. Similarly, we have third example benzene 1,3-diol is the IUPAC name of that compound. In common name, its common name is resorcinol. And our fourth example is 1,4-diol, which is the IUPAC name of that compound, and hydroquinone is the common name of that compound. Now we will read the physical properties of alcohol. Most of the common alcohol up to 11 or 12 carbon atoms are liquid at room temperature. Methanol and ethanols are free-flowing volatile liquids with characteristic fruity odors. The higher alcohols, the butanol, though the decanols are somewhat viscous, and some of a highly branched isomers are solid at room temperature. These higher alcohols have heavier but still fruity odor. Propane 1-ol and propane 2-ol fall in middle with barely noticeable viscosity and the characteristic odor often associated with a physician's office. Table 10 lists the physical properties of some common alcohols. So in this physical properties of selected table of alcohols, first alcohol is methyl alcohol. Methyl alcohol is the common name and methanol is the IUPAC name. Its molecular formula is CH3OH, and the melting point is given over here is 97 degrees Celsius and boiling point is 65 degrees C, and the density is 0.79 gram per ml. In this table there are lot of examples but I read only the data of methanol. Now we will discuss the boiling point of alcohols. Because we often deal with liquid alcohols, we forgot how surprising it should be that the lower molecular weight alcohols are liquid. For example, ethyl alcohol and propane have similar molecular weights, yet their boiling points differ by about 120 degrees Celsius. Dimethyl ether has an intermediate boiling point. The ethanol has boiling point is 78 degrees Celsius, and dimethyl ether is minus 25 degrees Celsius, and propane has boiling point 42 degrees Celsius. Such a large difference in boiling point suggests that ethanol molecules are attracted to each other much more strongly than propane molecule. Two important intermolecular forces are responsible. First is hydrogen bonding and second is dipole-dipole attractions. Hydrogen bonding is the major intermolecular attraction responsible for ethanol's high boiling point. The hydroxyl hydrogen of ethanol is strongly polarized by the bond to oxygen, and it forms a hydrogen bond with a pair of non-bonding electron from the oxygen atom of the another alcohol molecule. Ethers have two alkyl bonded to the oxygen atom, so they have no OH bond, or we can say OH hydrogen atom to form hydrogen bond. Hydrogen bond have a strength about 21 kilojoule, that is 5 kilocalorie per mole, weaker than a typical covalent bonds of 300 to 500 kilojoule, but much stronger than dipole attractions. Dipole attractions also contribute to a relatively high boiling point of alcohols and ethers. The polarized CO and HO bonds and the non-bonding electrons add to produce a dipole moment of 1.69 dBi in ethanol, compared with the dipole moment of only 1.08 dBi in propane. In liquid ethanol, the positive and negative ends of this dipole align to produce attractive interactions. We can compare the effect of hydrogen bonding and dipole-dipole attractions by comparing ethanol with dimethyl ether. Like ethanol, dimethyl ether has a large dipole moment and 1.30 dBi, but dimethyl ether cannot engage in hydrogen bonding because it has no OH hydrogens. The boiling point of dimethyl ether is minus 25 degrees Celsius, about 17 degree higher than that of propane, but still 103 degree lower than that of alcohol. Hydrogen bonds are clearly much stronger intermolecular attraction than dipole-dipole attractions. So this is today's topic regarding the alcohol.